Hey everybody, welcome to week 8 of PS 398. Week 8. By the end of this lecture, you will be halfway done. That means that we're halfway into this experiment. You know, I haven't tried to talk about it too much, but it is not lost that this is a somewhat unorthodox way to try to get around some of the constraints that we're all experiencing at the moment. And I've been thinking a lot about, what teaching might look like moving forward. And I don't have any particularly strong thoughts on that, so I thought it might be fun to try to do something educational. And it's gotten me thinking a lot about the teachers that I had that meant a lot to me. And I'm quite sure that some of them would think that these videos are the dumbest idea they've ever seen. I had a math teacher when I was a little kid named Sister Rosalinda. I'm sure she's since left us. She was like the best math teacher ever. And I'm pretty sure that all this fun and hijinks and tomfoolery, this would be something that she would not be on board with. I mean, she was Sister Rosalinda. She had a way of making things, she really brought out the interesting things that lived underneath the blackboard. And she would just sort of stare at the blackboard, like she couldn't say pause the video. So she'd just write something on the board and then just kind of stare at it like this. And by the way, Sister Rosalinda was the coolest. So she'd do that, and she had the sort of nuns that we had at my school. The habits that they wore were sort of they had a big rosary, and so sometimes she'd even sort of like twirl the rosary a little bit for effect while she was waiting for one of us to have that moment of inspiration, that those pause the video moments. I've been thinking about her a lot because I really wish that somebody would have thought to videotape her, because it would have been amazing. I'm gonna steal a page out of an important playbook. So you don't have to pause the video or anything, but I'm sure a lot of people in your life would be very proud of how much you're pushing through all of some of you are taking 5, 6, 7 classes. Some of you are doing this while you're working a full-time job. Some of you are doing this from home, or you're doing it from incredibly isolated situations. Some of you are doing it during or after being hit by this illness that's got everybody on the ropes. There are people that would be very proud to know how hard you're working. And I just hope that you'll spend 10 seconds thinking about them. I'll watch the time. You don't have to call them or anything, but I'm sure that it would mean a lot to them to know that you thought of them just now. I told you this was going to be a boring introduction, didn't I? Welcome to Nash 2. Today is not a lecture that's going to help you with dinner parties, okay? Like, you're going to go to dinner parties, there's going to be brie, there's going to be pigs in a blanket. This is just me envisioning. I don't know what actually happened. I talk about dinner parties all the time. I never go to dinner parties. It might not be obvious to you. So I don't know what happens at the dinner parties, but I do know that people don't talk about mixed strategy Nash equilibrium at dinner parties unless it's a dinner party that I don't feel envious about not being invited to, right? They're supposed to be talking about issues of the day. They're supposed to be talking about what they read in the New Yorker. They're supposed to be talking about a provocative 10,000 worder that they read in the Atlantic. This is what people do at dinner parties. I'm thinking. Exchanging all precious gifts, thinking that they got it made. It's going to be a long day, isn't it? Chewy is just sitting right there, staring at me like, what the hell is wrong with you right now, Dad? I have no idea what happened to you. You used to be sane and normal, and now look at you. You're crying thinking about Mr. Rogers, talking into a can. And then you're going to be crying all week when you edit the movie because you thought about Mr. Rogers. For this you're paying. So mixed strategy Nash equilibrium is not going to help you at dinner parties, but it's going to help you whenever you need to make a prediction in any model. People at dinner parties don't talk about matching pennies because then they'd have to talk about mixed strategy Nash equilibrium, which is not very exciting. They'd rather be talking about other things. However, it's really important. And it's actually super important not just for technical reasons. It is not just important because there's always a prediction. We'll talk about that in the A block. It's important because it takes full advantage of all of the assumptions that we've made up to this point. So up to this point, we've made assumptions on the individual players, which might be states or leaders of countries or opposition groups or firms or whatever, we've made assumptions that they have preferences over outcomes that are reflexive, complete, transitive, continuous, and independent. We've assumed that they know the game and that they know that everybody knows that they know the game. We've assumed that their preferences are imposed on the Cartesian product of action sets so that the inputs of their decision model are combinations of people's choices. This is game theory. We've made all these assumptions and we actually haven't squeezed all that we can out of them. And mixed strategy Nash equilibrium is where everything kind of comes together and we take full advantage of this beautiful structure that was built for us by so many of the great people that came ahead of us. I'm not going to be able to deliver a whole lot of huge substantive punchlines. There won't be any ASMR moments when I'm talking into the microphone reading a blurb about how awesome this all is. However, if you look real hard, if you pay special attention, if you just let it get you, there will be some cool moments in today's lecture. I hope. So let's get to it. I actually want to talk about mixed strategy Nash equilibrium by way of 3 examples that are relevant for international relations. Every time I'm going to layer additional things on top, but I only want to talk about 3 examples. Your problem set will include some more examples and then one extended example that will lie outside of what I've showed you. However, I will try to design the problem so that it takes you through step by step, through an analysis that nobody would ever reasonably expect you to be able to do. You won't see anything like that question on your final. You might see a regular 2x2 example on your final. So in the A block, I want to talk about matching pennies. We have that loose end from the last lecture, right? So we wrote down matching pennies, and it turned out that there was no pure strategy Nash equilibrium. That's really annoying. That means we wouldn't get paid from the funding agency that asked us to find all of the wonderful things, the predictions that one could make based on matching pennies. So if we want to get paid, we need to figure out how to make a prediction using matching pennies. So we will resolve that particular tension in the A block. In the B block, I want to talk about Bach or Stravinsky, the coordination game, and actually I want to talk about coordination as a continuum. I want to talk about the different kinds of coordination. I actually want to embed regular coordination, beep beep, and Bach or Stravinsky coordination, do 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 do. That's Vivaldi. That's not Bach. Bach is do 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 do. That's not Bach either because you're tone deaf. Bach goes do 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 do. This is all very embarrassing, Chewy. And actually, you'll see that after we've fully exploited everything there is to exploit about Nash equilibrium and expected utility, coordination and Bach or Stravinsky are 2 cousins in one big family of coordination, and mixed strategies and coordination games are kind of interesting, and we'll be able to really see how it all goes together. And then in the C block, I want to talk about chicken, which it's almost lunchtime here, so it was bound to find its way in somehow. Chicken is really important in terms of nuclear brinkmanship, and it's a useful way for us to think about the difference between pure and mixed strategy Nash equilibrium in terms of their substantive ramifications. Right, so we're only going to be able to talk about some of these things qualitatively. We're only going to be able to talk about essential differences. Not every quantitative difference is going to be relevant, which is fine. But no matter what, the punchline is going to be, we really don't like this mixed one vis-a-vis the 2 pure strategy Nash equilibria for reasons that you'll see momentarily. So 3 examples relevant for international relations, exploit the full structure of expected utility, do awfully at dinner parties. Sounds like it's going to be a great day together, doesn't it? Let's get started. So suppose that we were playing Matching Pennies. You just got to bring the energy. The rest is up to you. All I can do is give you energy. All right, so remember, there's 4 strategy profiles of Matching Pennies. The idea is that I have a penny and you have a penny, and we secretly determine whether it's heads up or tails up, right? And the idea here is that I wanted them to both be heads or both be tails, in which case I win a whole penny off of you. Oh boy, don't spend it all in one place. And you want them not to be, you want it to be a heads and a tails or a tails and a heads. So I want to coordinate, I want to hang out at a wedding, and you want to not coordinate. You actually hate me and don't want to hang out at the wedding, and you're really tired of all this awful time I spent at the wedding talking about mixed strategy Nash equilibrium. You're like, I thought we agreed never to talk about this at dinner parties, weddings, or other events. So on the diagonal, I get 1 happiness point and you get -1 happiness points. And off the diagonal, I get -1 happiness points and you get 1 happiness point, right? And you'll remember that this game has like a big cycle in it, right? So if we start at heads, so at heads, right? So I'm happy here. We're hanging out at the wedding. I think this is great. You're really unhappy. You're like, oh, I could have deviated and gone and hung out at the carving station and I wouldn't have to put up with this person. And you could have, so you deviate. So heads is not a Nash equilibrium in pure strategies. So you could deviate, right? So now we're at heads-tails. And I see you over at the carving station. And I'm like, I want to hang out with this person. We could be really good friends. We could be musical companions if we play our cards right. So I could deviate, right? From heads-tails, I'm thinking conditional on you playing tails, I could have played tails, right? And then we'd be together. We'd be hanging out. I could talk about mixed strategy Nash equilibrium with you. Now, okay, so heads tails is not a pure strategy Nash equilibrium. How about tails tails? Well, tails, you're like, I'm tired of this person bloviating so much. I wish, if conditional on him playing tails, I wish I had played heads. I'm tired of this Leslie Knope mishigas. Stop handing me binders, right? So that isn't a pure strategy Nash equilibrium. So then the last one to rule out is tails heads. You're happy, I'm unhappy, conditional on you, I wish that I had played heads. So none of these pure strategies is a Nash equilibrium, which means that the funding agency wanted us to understand, hey, how do people behave at weddings, / how do generals figure out tactics on the battlefield? We wouldn't have a prediction yet. So that's no bueno. So we need to come up with another way to get it. Okay? Now, I want to observe that if either of us played a pure strategy, if I played heads, your best response would be tails in pure strategies. You wouldn't mix, right? If you knew that I was in the heads row, you would just go to tails for sure. You would run for the hills or the carving station, as if I'm not the one at the carving station in this scenario. Of course I'm at the carving station. Prime rib. Apparently this is a really nice wedding. So you would respond in pure strategies to me playing heads. You would respond in pure strategies. If I played tails, you would just run to heads. And if I knew that you were playing heads, I would run to heads. We would only respond to a pure strategy with a pure strategy. Okay? In order for us to mix, we both have to want to mix, right? It's not just one of us that's going to mix. It's not like you're going to play heads with some probability and tails with some probability, and then when I play heads for sure, you're gonna wish that you had defected, because that means that some of the time you're stuck with me. That's no bueno. So suppose that row player, that's me, the Leslie Knope type, plays heads with probability P and plays tails with probability 1 minus P. So the idea here now is suppose that there's a random number generator. Suppose that you, instead of making a choice, joom, I go heads, joom, I go tails. Suppose that you didn't do that. Suppose instead that what you did is you said, I'm going to program a computer with a certain kind of probability structure. I'm going to tell it to tell me to play heads a certain percentage of the time, and I'm going to tell it to play tails a certain percentage of the time. Okay? Row player is now mixing it up, right? They're like, some of the time I'm going to go heads, and some of the time I'm going to go tails. I'm going to keep column player guessing. I'm going to make sure that they don't know for sure what I'm going to do, because every time I show up somewhere, it seems like they want to avoid me. What's with that? So I'm going to mix it up. This is obviously a great way to get a friendship started at a wedding. And you're going to mix it up too. So suppose that you played heads, your column player. Suppose that you played heads with probability Q. All right? So you're going to choose a Q that tells us how often we're in the heads column and how often we're in the tails column. That'll be 1 minus Q. Right? So we could work out the probability of being in each of the 4 cells if we were so inclined. Right? So the probability of being in heads is P times Q. The probability of being at heads tails is P times 1 minus Q. The probability of being at tails heads is 1 minus P times Q. And the probability of being at tails is 1 minus P times 1 minus Q. So these probabilities, just all it is just mixing it up. Instead of making a choice, now you choose a probability. And the question is going to be, what's a best response? How do I choose the best P in response to your Q? And how do you choose the best Q in response to my P? That's the whole idea here, is we're going to come up with best response correspondences. I'm not going to spend too much time on it. I need to figure out, for every possible Q that you could choose, for every Q that you could choose up here, I need to figure out what P I would like to choose. All right? This is actually a lot more simple than it seems right now. I'm describing it awfully. So why don't we calculate some expected utilities? Why don't we calculate my expected utility of playing heads, which is going to depend on Q, and my expected utility of playing tails, which is going to depend on Q. And we'll calculate your expected utility of heads, which is going to depend on P, my mixing probability, and your expected utility of tails, which is going to depend on P, my mixing probability. Very well. So, row player, their expected utility of playing heads. Well, with probability Q, they're at heads then, which means they get 1 happiness point. So Q times 1. And then with probability 1 minus Q, they're in the heads tails cell, and they get -1. So Q times 1 plus 1 minus Q times -1. And you can work that out, and that works out to 2Q minus 1. The expected utility of me going to heads as a function of your mixing probability is 2Q minus 1. Okay? Let's think about my expected utility of going tails. Apparently now I'm underhanded. Right, so my expected utility of playing tails, well, with probability P, we're at tails heads. I'm sad. I wish I had gone to the carving station. So it's Q times -1. And then with probability 1 minus Q, we're at tails, and all is right in the world again for me. So that's 1 minus Q times 1. You work that all out, and that adds up to 1 minus 2Q. If my expected utility of playing heads is strictly greater than my expected utility of playing tails, then my only best response is to set P equals to 1, which is to say play heads for sure. All right? I'm going to choose the thing that I'm going to choose the lottery. You just made a lottery for me. Your Q made life a lottery ticket to me. I don't get to know if where we are. I don't get to know if we're together at the wedding or if we're apart at the wedding or if we're together on the battlefield or apart on the battlefield. I don't get to know that. It's a lottery ticket. And I'm going to choose which. If there's a lottery ticket that gives me a strictly greatest utility, I'm going to choose it. All right? So in other words, if you choose a Q strictly greater than 1/2, if you're playing heads strictly more than half the time, then the only thing that I want to do is play heads for sure, set P equal to 1. Similarly, if my expected utility of tails is strictly greater than my expected utility of heads, which is to say if Q is strictly less than 1/2, right? Then the only thing I would want to do is play tails for sure, which is to say set P equals to 0. But notice that if you happen to choose Q exactly equal to 1/2, if you happen to choose just the right Q, the 50-50, heads carving station, tails dance floor, actually the best way to not find me at a wedding is to be on the dance floor. If that's your choice, if you chose exactly 50-50, if you set Q equal to 1/2, then I don't care. I could mix any way and it would give me the same expected utility. Right? Think about it. Right? So that means that the expected utility of heads is equal to the expected utility of tails. Why? Because 2Q minus 1 equals 1 minus 2Q equals 0. Now, if I mixed it up, if I went heads some of the time and got 0, and tails some of the time and got 0, then I get 0. I don't care. Whatever the P is, I get 0. Right? I'm mixing over two things that I'm completely indifferent between. This is actually important. All right? So if Q is exactly 1/2, then I could choose any P. I could choose any P greater than or equal to 0 and less than or equal to 1. I could, that whole unit interval, 0, 1, with brackets. So that's my best response correspondence. My best response correspondence is if Q is strictly less than 1/2, set P equals to 0. If Q is strictly greater than 1/2, set P equals 1. Go heads for sure. But if Q is exactly equal to 1/2, any P will do. Oh, that's way too hot. That's way too big of a sip. You may be wondering, because this is now like a character in some of these movies. This Yeti is full of very hot water with nothing but lemon and honey in it, because my instrument requires constant care. Just took a really big sip. Ugh. Burned tongue feeling. Woo! Not in equilibrium. Well, let's do the same exercise for you, for column player. And this means it's going to read in my probability. It's going to read in P and spit out the best Q. All right? Well, let's think about these expected utilities. When is the expected utility of heads strictly greater than the expected utility of tails? Well, that's if P is strictly less than 1/2. If I'm unlikely to go heads, strictly less than 1/2, then you're going to try to avoid me by going heads all the time. That means sometimes you're stuck with me, but it's less than half the time. More than half the time, you don't have to listen to me talk at you. Similarly, if P is strictly greater than 1/2, then if I'm going to heads more than half the time, that's here, not here. If I'm going to heads more than half the time, right, then you want to go to tails. So you'll set Q equals to 0. And you'll go tails all the time. 1 minus Q is 1. You'll play tails with probability 1. You'll play a pure strategy. However, if P is exactly equal to 1/2, if I'm at the dance floor half the time and at the carving station half the time, then you're indifferent too, and any Q will do. So your best response is set Q equal to 0 if P is strictly greater than 1/2. Any Q will do if P is exactly equal to 1/2. And set Q equals to 1 if P is strictly less than 1/2. I mean, so there's these best response correspondences, and I know that this is officially what we're talking about, and it might be a little bit Spartan, but the story is a little bit more compelling. Remember, no pure strategies here, so these probabilities, they might seem trivial, but they're really important right now. They're our last hope. Pure strategies didn't get us anywhere with matching pennies. So we have these two best response correspondences, and something would be a Nash equilibrium if, so let's say that I was at some P. Just choose a P arbitrarily, choose some P. Now let's think about your best response to that P. It might be 0, it might be 1, or it might be anything. If I chose P equals 1/2, it might be anything. Now let's think about my best response to yours. Well, your best response, chances are, is a pure strategy, in which case I want to switch to a pure strategy. I don't want to mix. I want to find you for sure. However, if your best response is the mixing thing, then anything I would do would be fine. So in particular, if my indifference leads to your indifference leads to my indifference, now we got something. It's weird that sentence doesn't really make a whole lot of sense, but it actually makes perfect sense. So in other words, we need to see if there's a P that's the best response to the Q that is the best response to it. It'll be easiest to do that graphically. So let's put all of these, let's get rid of all this. So let's just get rid of all these accoutrements and just focus only on the P's and Q's. So we'll draw a square. I don't know why this one deserves one of these instead of one of these, but. All right, so on the horizontal axis of this square, I've got P, which is how often row player, me, plays heads. And on the vertical axis, I've got Q, which is how often you, column player, play heads. All right? Now, the first thing I want to say is that the four corners of this square are the pure strategy profiles. Think about it. So if P was equal to 0 and Q was equal to 0, well, that would mean that that's tails, tails. It means you're never playing heads. Is that here? Yeah, that's here. And then up here, this is P equals 1 and Q equals 1. I'm sure I'm like way off camera. Like, well, that's heads, heads. Right? P equals 1 and Q equals 0. That's heads, tails. There's tails, heads. These are the four pure strategy profiles. This is something that really highlights the fact that that we as analysts are doing something fundamentally different than the people that we're studying, right? So chances are excellent that, with the exception of maybe some think tank people or some consultants to get brought in, or maybe some of the mathematicians that live deep inside of some of the government bureaucracies, most people aren't thinking about it this way. This is just us getting to the bottom of it in our own way. This is our plea for understanding. So let's plot role player's best response in this space. We're going to draw a line that represents the best P in response to every Q, right? So here's all the Qs. Here's Q equals 0. Here's Q equals 1/2. This is going to be important. And here's Q equals 1, right? Here's P equals 0, P equals 1/2. It's going to be important as well, and P equals 1. All right, so if Q is low, if Q is strictly less than 1/2, if we're south of this line, if Q is strictly less than 1/2, then the best thing for role player, apparently my Pittsburgh accent decided to make an appearance. So the best thing for role player is for us to set P equals to 0. I guess I wasn't going to be able to make 3 hours of videos every week for 15 weeks and then not have my accent come out. Similarly, if Q is high, right, if we're north of the line, if we're strictly north of this 50-50 line, then the best thing, that means that I suddenly want to go from the dance floor to the carving station, right? So I'm going to set P equals to 1/2. So I have vertical lines here and here, right? And these represent my pure strategy best responses, right? Even if you play a mixed strategy, I have a best response in pure strategies most of the time. I'm either at 0 or I'm at 1. Those are pure strategies. However, that wasn't even a straight line. So not only did I miss in terms of this, but there's no way that this line is a parabola. But along this line, which I'm sure I just missed again, any P will do. Any P. I could choose any P. This is the whole P axis. Here's the whole P. I could choose any P. Any P. Any P will do. Remember, that's me choosing between mixing over 0 and 0. Any P, no matter how I slice it, I get 0. I'm indifferent. Any P will do. This is really important. All right, so it goes zhing, 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 right? Zoop, zoop, zoop. I don't know what the appropriate sound effect is. Taka, 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 taka. I don't know. Okay. I swear, I didn't have more coffee today. This is just me. This is the halfway point for me. So let's do column player next. They're thinking if P is low, so they're up here. They're riding that Q equals 1 line. This is heads for sure, right? Similarly, if P is strictly greater than 1/2, so that we're to the right of this 50-50 line, then suddenly they're like, oh no, thank you, I will be on the dance floor. I would like to avoid this person. So they go tails for sure. Pure strategies. These are their 2 pure strategy best responses to most of the P's. Most of the P's. All of the P's except for the one very special P of P equals 1/2, where any Q will do. Right? So any Q will do. So now we've drawn out these best response correspondences. Notice that they don't intersect at any of the 4 corners. At every corner, one person would like to be in that corner, but never 2. Right? So role player is happy at these 2 corners. The 0, 0 and the 1, 1, the places they're together. And column player is happy at these corners, the 1, 0 and the 0, 1. I think I got that wrong. The 1, 0 and the 0, 1. Those are the ones where they're apart. So this has the whole story in it. This is the whole story, is in this stupid square. But at exactly 1/2, 1/2, they intersect. That's a mixed strategy Nash equilibrium. That's the only Nash equilibrium matching pennies, is go heads half the time, go tails half the time. That's equilibrium. That's equilibrium. The best P in response to the Q in response to the P. The best Q in response to the P in response to the Q. They're best responding to one another. That's an equilibrium. They're maximizing their expected utility. Or in that case, they're saying, I'm indifferent. You chose just the right P and it made column player indifferent. And column player chose just the right Q and it made row player indifferent. And that indifference, that indifference, the fact that any P would do and any Q would do, is exactly the thing that let these things cross. Otherwise, there wouldn't have been any crossing. That's an equilibrium. We have finally saved ourselves with Matching Pennies. We can show up to the funding agency with something in our hand. We would show up and say, we predict that half of the time row player will go heads and half of the time they will go tails. And half of the time column player will go heads and half of the time they will go tails. That's it. That's an equilibrium. That's a mixed strategy Nash equilibrium, not a pure strategy. The pure strategies are on the corners. Right, that's a mixed strategy Nash equilibrium, or just a Nash equilibrium. Remember, because of degenerate lotteries, pure strategies are just special cases of these mixed strategies, right? That's these corners. And so consequently, if I ever just say Nash equilibrium, I mean in pure or mixed strategies, because now that we're here, they're all the same. So here's a very important result, and the reason that his name is on his eponymous theorem. Nash's theorem tells me that if a game has a finite number of players, like 2, and a finite number of alternatives for each player, like 2, so player A, player B, and each can go heads or tails, so that's 2 by 2, finite, 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 that's as finite as it gets. Every game like that, finite number of players, each equipped with a finite number of options, has at least one Nash equilibrium, be it in pure or mixed strategies. That's why the theorem's named after him. He showed that. That means that any analysis that you started in this style, you would be able to proceed knowing that it wasn't a wild goose chase. You'd be able to proceed knowing that at minimum, it was a solvable problem. That's why it's such an important result. It's a solvable problem to find the equilibria, right? You can find the equilibria because everything has at least one. So if you set a computer running, if I set my computer running to find all the pure strategy Nash equilibria of Matching Pennies, it would run forever. It would never find one. Right? I would have just wasted a whole lot of computing power that I could have spent playing Civ 6. Instead, I should have gone looking for mixed strategy Nash equilibria, which it would have found instantaneously at 1/2, 1/2, 1/2, 1/2. So while we're here, let's just be a little bit more formal about these things. So a mixed strategy is just a function, right? It reads in alternatives for me. So my mixed strategy, row player strategy, reads in each of row player's options, go heads or go tails, and assigns every one of those a probability. Instead of me playing heads for sure, tails for sure, I have a function. Let's call it little sigma, sub I, sub Rob, sub row player, sub 1, whatever. And what it does is it reads in capital A for that person. It reads in their available actions, and it spits out a probability to play that action. So in other words, a mixed strategy for me is just a set of numbers, every one of which is non-negative because it's a probability. Probabilities can't be negative. And they have to add to 1, right? So, and there have to be as many of them as there are choices for me to make. So if I have 2 things to choose over, I need P and 1 minus P. Right? They have to add to 1. I need to find some P greater than or equal to 0 and less than or equal to 1, and then 1 minus P is the probability of the last option. If it had been 3, I need a P1, a P2, and a 1 minus P1 minus P2, and so on. A mixed strategy for me is just a way of assigning every one of my options a probability. What that does is it generates a massive lottery. It generates a massive lottery where every possible outcome of the game, heads, 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 tails, tails, heads, tails, tails, where every possible outcome of the game, every one of those gets hit with some probability, and it's like the product of everybody's probability of playing the action that they would have to get to that, right? So for heads, heads, the probability of me enjoying that 1 happiness point that I get at heads, heads is 1/2 times 1/2 in equilibrium. So 1/4 of the time we're at heads, heads. So my expected utility is 1/4 times 1 for heads, heads, plus 1/4 times minus 1 for heads, tails, plus 1/4 times minus 1 for tails, heads, plus 1/4 times 1 for tails, tails. That's just 0. I was indifferent. Remember, I was indifferent. When Q was 1/2, I got expected utility of 0 no matter what. Right? So of course it's 0. I have nothing to deviate to. If I went heads instead of mixing, I'd get 0. By definition. If I went tails instead of heads, I'd get 0 by definition. So I have no profitable deviation. and you have no profitable deviation. Why? Because, well, right now you're getting 0. 1/4 times -1 for heads heads. 1/4 times 1 for heads tails. 1/4 times 1 for tails heads. For heads tails. For tails heads, I'm sorry. And 1/4 times -1 for tails tails. So your expected utility is 0 too. Now that just happens to be true. That doesn't have to be, it's not always symmetric like that. But the idea here is that you have no reason to deviate because that's your expected utility for each of the things you're mixing over. A necessary condition for being willing to mix over 2 or multiple strategies is that you're indifferent between them. Otherwise you wouldn't be willing to mix, you'd just play the best one for sure. So in order to be willing to mix, your opponent must have rendered you indifferent between the things that you're mixing over. That's fascinating. Where's the dinner party? I'm ready. Call Sun Tzu and let's have a dinner party. So I can just write everybody's mixed strategy is just little sigma, right? And it's like little sigma equals sigma 1, that's my probability function. Sigma 2, that's your probability function. Sigma 3, that's Chewy's probability function. Sigma 4 is Lucy. Sigma 5 is Chancellor Jones. Right? So I can just write sigma, and that's everybody's way of mixing over their available actions. And we can define expected utilities on that because all it does, just like we just did, all it does is say, okay, give me the probability of each of the elements of A. Right? Tell me the probability of getting to strategy profile A, and then multiply the utility that each person gets at that profile times the probability of getting there and add them up. That's an expected utility. So one of these sigma profiles is a mixed strategy Nash equilibrium if nobody has an incentive to deviate to some other sigma. So we say that sigma is a Nash equilibrium if the expected utility the player I gets for playing sigma I against little sigma minus I, everybody else's mixing probabilities, is greater than or equal to the expected utility that they would get for deviating to some other sigma I prime against sigma minus I. So if I knew what everybody else was doing in terms of the mixing probabilities, I have to find the sigma that is among my best things to do there in terms of maximizing my expected utility. If that's true for every I, then we have a Nash equilibrium. So we have it, you're not going to have to draw one of these squares every time. The squares are a little bit annoying, although they're very useful, pedagogically speaking. But, the big thing here is to check a Nash equilibrium. What you do is you say, well, okay, let's say I'm mixing over heads and tails and you're mixing over heads and tails. Let's name the associated probabilities, P1 minus P, Q1 minus Q. Now we know that the only reason that I would be willing to mix over heads and tails was if you chose the Q that would make me indifferent over heads and tails, which in the last example was 1/2. Similarly, if you were willing to mix over heads and tails, then I must have chosen my P in such a way that you were indifferent over them. Otherwise, you wouldn't have mixed over them. Next thing you know, this is a little bit easier because all you have to do is find these two expected utilities and check to see when they're equal. And then the big thing is, what you have to do finally is then after you've done that, calculate the associated expected utility, which in this case was 0, and say, does anybody have a profitable deviation? Well, in a 2x2 game like this, no, because deviating to heads is the exact same thing. Deviating to tails is the exact same thing. Choosing another probability, well, you're indifferent over all those probabilities, so it's the exact same thing. On your problem set, you're going to have a slightly trickier one. It's not worse than tedious. There may be moments where you lose track of your bookkeeping, and you do have to be kind of careful to make sure that you're saying, well, I'm being deductive right now, and let's look for an equilibrium of this type, and then check, see if every necessary condition is satisfied, and then once the test is passed, rightfully name something a Nash equilibrium or not. There's a lot of little steps there, and it's going to take you time to learn those little steps. But none of this is what I would consider conceptually difficult. This is more just like a here's how you do it. Bump, 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 bump. Apparently that's the soundtrack for how you do it. Bump, 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 bump. Now, if we think about this from a tactical standpoint, if we're thinking about matching pennies from the idea that you want to keep the enemy guessing, well, then of course you have to mix. If we're watching Braveheart and there's the very strong English army and the less strong Scottish army, the Scottish army doesn't want to show up on the same battlefield at the same time. They want to strike from the shadows. They want to play Assassin's Creed, not Call of Duty. Well, then they couldn't ever go. It wouldn't make any sense for the guerrilla army to just go to one place, because then the strong army would just show up there. So in order to keep the opponent guessing, you have to engage in probabilistic play. Mixing it up this is what it looks like. Keeping the enemy guessing, this is what it looks like. Right? This is a mathematical crystallization of that ancient idea of keep the enemy guessing. I'm ready for the dinner party. The dinner party may begin at any time. I'm not talking to anybody. I'm talking to my ring light. This is what we've gotten to in 2020, is I'm talking to my ring light. So that's a mixed strategy Nash equilibrium. I want to do 2 more examples and I want to squeeze more out of them, but if you can get this, and if you can understand what mixing means, if you can think a little bit about that, then that's pretty great, right? This is a subtle concept, but it also, if you see it from the right angle, it makes some sense. So let's just keep our practice up. So in the B block, I want to talk about Bach versus Stravinsky. Let's go to the B block. All right, let's do it again. Bach or Stravinsky? You know who never had any trouble getting invited to dinner parties? Actually, I don't know if that's true. Regardless, nice to see you again, gentlemen. Hope you're having a great day today. So now we've switched from a game of anti-coordination, matching pennies, I don't want to see you at this wedding, to a game of coordination. We want to show up to the same concert, right? You like Bach, I like Stravinsky, but we're musical companions. We only like to watch music together. I hate the thought of listening to The Rite of Spring. No matter how much it means to me, it only means something to me if you're there. And no matter how much you enjoy Toccata and Fugue, no matter how deeply that hits you in the soul, you only want to watch it with me. No accounting for taste. So we want to coordinate. Nope. We want to coordinate. We want to be at the same show, but we have different opinions about what kind of show we want. Now, I just want to mix it up. I just want to make this a little bit interesting. And you're like, oh no, that sounds bad. So right now, think about what we have with the vanilla version of Bach or Stravinsky. You get 1 happiness point for being at the show that you don't like as much. You get 0 for being alone, and you get 2 for being at the show that you like with your musical companion, right? Okay. Now, throughout, I have said as often as I can that the numbers don't really matter. It's the rankings that matter. However, expected utility actually gives us scales. The scales matter. It's ironic that I chose the music one for this. So the scales matter on expected utility in ways that they don't matter for little u regular utility. Bernoulli utility is the fancy. So I just want to kind of exploit that to give you to show you like how a comparative static result would look if you decided to try to model the utilities. What does any of that mean? So suppose that we decided that we wanted to parameterize how much you like one composer more than the other. So right now we're saying the gap in happiness points is 1, right? So if I'm at Stravinsky, I'm nerding out, I love it, I get 2. If I'm at Bach with you, I'm a little bit bored, I might yawn, I get 1. Who's to say that 1 is the right gap? So right now I'm going to say that the gaps matter. I'm officially announcing that the gaps matter right now, okay? We can toggle out of that later, but right now the gaps matter. The scale matters. So the difference between 2 and 1 is not the same as the difference between 3 and 1, or 4 and 1, or 5 and 1. So right now, let's say that instead of 2 happiness points for you at Bach, let's say that you get 1 plus C for composer, like for your favorite composer. You get 1 plus C, where C is some number greater than or equal to 0. So if C was exactly equal to 1, we would have regular Bach or Stravinsky. If C was equal to 0, we would have coordination game with cars. If C was huge, then you would like Bach way more than Stravinsky. Okay? So we're going to measure some intensity right now. Similarly, I like going to Stravinsky. Instead of 2, let's call it 1 plus C. So let's assume that we have a symmetric bonus. We enjoy our preferred composer. Our gap between our favorite composer and our next favorite composer is the same happiness gap. C. It might be 0, it might be a Googleplex, who cares? Well now, Now we've kind of parameterized it. Now we have a game that depends. We have a game that depends on how intensely we like our favorite composer versus our not so favorite composer. It's really just to keep it interesting, right? If at any time in this block you go like, oh no, I'm not sure what's happening, just set C equals to 1. Just set C equals to 1 and you got regular old Bach or Stravinsky. It's okay. Or just set C equals to 0 and you have regular old coordination game, and that's fine too, right? I just want to say, what happens if we squeeze a little bit more out of this? I want to squeeze it. What happens if we really squeeze all that we can out of this analytic structure that we've built? So you might think that the fact that we have all the pure strategy Nash equilibria, you might remember that Bach, and Stravinsky are both pure strategy Nash equilibria. Maybe you think the analysis is done. We don't have nothing. We have something to take to the funding agency. In fact, we currently have too many things. It would have been great if we only had one prediction. Right? Now, I'm saying there's another one. And you're like, how do you know? Here's a cool result. This is a cool result. Don't ask how you prove it. It's hard. This is hard. Nash's theorem, if you did nothing but think about Nash's theorem for about 3 months, you'd be able to prove it. This other one, it would take a lot longer. But here's a cool result all the same. Almost all games of this form, if I used a random number generator to come up with these numbers at random, right, if these utility numbers, almost all games, with probability 1, the number of Nash equilibria in pure and mixed strategies is odd. I got 2 equilibria right now. I got 2 equilibria. I need to find some more. Because chances are excellent, which is to say chances are really excellent, that this thing has another equilibrium somewhere. I can construct a game that has an even number of equilibria, 2, 4, 6, 8. I can come up with a game that has an infinite number of equilibria. They're very rare. They're rare. They're rare in a very strong sense. All right? So if I show you a game that has only an even number of equilibria, you are on pretty firm footing. You're on very firm footing saying to yourself, I think there's probably a mixed strategy equilibrium in there somewhere. And that's what I'm thinking right now. I'm thinking I only got 2 equilibria. Chances are good there's 1 or 3 or 5 or 7 more to get me up to an odd number. So along those lines, notice that both players have best responses to pure strategies that are pure strategies, right? So if you were playing Bach for sure, I would play Bach for sure. If you were playing Stravinsky for sure, I would play Stravinsky for sure, and likewise for you. So there is no reason for us to think that the best response to anything that involves mixing is going to be pure, or the best response to anything pure is going to be anything that involves mixing. It's only pure versus pure and mixed versus mixed. So suppose that both players are mixing, which is to say, suppose that row player is going to Bach with probability P, and suppose that column player is going to Bach with probability Q. Well, let's think about row players' expected utility for going to Bach. Q% of the time, they're getting 1 happiness point. 1 minus Q% of the time, they're getting 0 happiness points. So it's just Q. That's an easy one. Their expected utility of going to Stravinsky, well, with probability Q, they're getting 0, so that's 0 still. With probability 1 minus Q, they're getting 1 plus C. They're getting 1 plus C. That's that 1 plus that little ding, that little Stravinsky bonus. Good band name. Not great, but good. Now, unfortunately, that means we have to do some of the first outside, inside, last. Oh my goodness. I thought I'd never have to multiply 2 polynomials before. Again. And you work it out and you get 1 plus C minus Q times 1 plus C. I mean, there's a lot of different ways to write it. So then we have to think about when is row player going to be indifferent between those two things. What's the Q that sets the expected utility of Bach equal to the expected utility of Stravinsky? What's that magic Q that's going to get us to the inside of the square? Right? What's that Q that makes row player indifferent between Q and 1 plus C minus Q times 1 plus C? And you work it all out, bump, it's Q equals 1 plus C over 2 plus C. The mixing probability the column player uses to render row player indifferent depends on this intensity of preference difference. The probability is going to reflect that. If it might be high, it might be low. It's going to reflect that intensity. The amount that we like our preferred composer, the intensity of our preferences in this bargaining problem. how winnery of a winner we would be vis-a-vis your losery loser of 1 depends on C. Well, let's work it through for column player. What's their expected utility of Bach? Well, their expected utility of Bach is P% of the time. With probability P, they get 1 plus C happiness points. They're at their favorite composer, so they get 1 plus that happiness point perk. And then 0 for being at Bach Stravinsky, so we don't have to worry about that. So that's just P times 1 plus C. And their expected utility of going to Stravinsky is, with probability P, they get nothing, so we don't have to worry about that. And with probability 1 minus P, they're getting 1, so it's just 1 minus P. So what's that magic mixing probability that row player could use to render column player indifferent between these two columns? Well, that's the thing that sets P times 1 plus C equal to 1 minus P. And you work it out, it's P equals 1 over 2 plus C. This is interesting. We haven't even squeezed all we can just yet, but notice that Q is getting bigger and bigger and bigger as C is getting bigger. So as C gets bigger and bigger and bigger, 1 plus C over 2 plus C gets closer and closer to 1. Because eventually that 1 and the 2, they start not mattering. If C was 1,000, who would care about the 1 versus 2? So then you'd have 1,000 plus 1 over 1,000 plus 2. That's pretty darn close to 1, right? So if C is really big, then Q is really close to 1, which is to say if C is really big, column player saying, I'm going to Bach because I love Bach. Bach makes me feel 1,000 happiness points happier. The probability reflects that. That's so cool. Notice also that row player, they're saying, as C is getting bigger and bigger and bigger, their mixing probability P is getting smaller and smaller and smaller. 1 over 2 plus C, as C gets bigger and bigger and bigger, that denominator is getting huge and we're getting closer and closer to 0. Next thing you know, they're basically never going to Bach. They're going to Stravinsky a lot. So this mixing probability gets bigger and bigger on the composer that you like more as that perk that you get gets bigger. That's pretty neat. Notice that if C was equal to 0, so that you were exactly indifferent between the two composers, it would just be a driving coordination game. 1, 1, 1, 1. And the mixing probabilities would be 1/2 and 1/2. So the coordination game is just like a limit point as that C goes to 0. This game converges to the coordination game with a 50-50. And as C gets bigger, so that these two composers become less and less comparable, you start liking the right side of the road a heck of a lot more than the left side of the road suddenly. As that happens, as the winneriness of the winner gets bigger, those mixing probabilities diverge. I think that we could have a spectacular, sparkling dinner party based on that alone. That's just me. That's a comparative static result again. That's how one thing responds to the other thing responding. Now here's something interesting. Let's work out the expected utility. What's the expected utility of this equilibrium for these two players? Let's do some welfare analysis. Well, in the mixed equilibrium, in the equilibrium that we just unearthed, well, we know that we can just use the simple formulas, right? So we have the expected utility for row player of Bach is just Q, and the expected utility for column player for Stravinsky is just 1 minus P. So you can work all that out, and what you wind up getting is the expected utility for row player for this mixed equilibrium is 1 plus C over 2 plus C, and the same for column player. So that's getting bigger with C as your benefit for the preferred composer gets bigger, so too does your overall happiness, but it doesn't go all the way. No matter what, 1 plus C over 2 plus C is strictly less than 1. Right? 1 plus C over 2 plus C must be strictly less than 1 no matter how big C is. It might get really close to 1, but it's always smaller than 1. It's always strictly smaller than 1, which is bad because that's how many happiness points you get for being the loser in the pure equilibrium. You get 1 happiness point. I got 1 happiness point at Bach, and you got 1 happiness point at Stravinsky. Right? So if we're bargaining here, this mixed one is always worse. This mixed equilibrium is Pareto dominated by the pure equilibria. Why? Because whoever is worse off at the pure equilibria, whoever is the loser of the bargaining process, whoever is the person that got 1 point is still doing better than they would have done. They're still doing better than they would have done in this mixed equilibrium. Why? The mixed equilibrium wastes. So why does it waste? Well, it wastes because let's work out the probabilities. Let's just say that C was equal to 1, just to make the math easy. Okay? So suppose that C was equal to 1. That means that row player goes to Bach 1/3 of the time and goes to Stravinsky 2/3 of the time. That means the column player goes to Bach 2/3 of the time and goes to Stravinsky 1/3 of the time. So how often do our musical companions watch the same show? Well, that's Bach, which happens with 2/3 for you and 1/3 for me. That's 2/9. And Stravinsky, that's 2/9. 2/3 for me and 1/3 for you. That's 2/9. So less than half the time we're at the same show together. Less than half the time we're at the same show together. 5/9 of the time we're at different shows. 4/9 of the time we're at the one where we're both at our preferred show but we're alone, so we don't get any happiness points. And 1/9 of the time we're at our least preferred show by ourselves, which is like the worst of all, except it's the same 0 happiness points. So 5/9 of the time we're not at the same show. We get 0 5/9 of the time. So this is very wasteful. This is very wasteful. As C gets bigger and bigger, we waste more and more. And that waste is what induces this. That's why the utility that you get for playing this mixed equilibrium in expectation is lower than the pure strategy Nash equilibrium payoff that you get for being the loser, only getting 1 happiness point. And it's far smaller than the expected utility that you get for being the winner. Right? So your favorite equilibrium is the pure strategy one where your favorite show. Your second favorite equilibrium is the one where we're at the same pure strategies at your less preferred show, and your least favorite is the mixing one because of all this waste. Notice, however, that the expected utilities in the mixed equilibrium are perfectly egalitarian. So if the role of the state is to choose an equilibrium, it can either make a winner and a loser, or it can be egalitarian. It can't do both in this model. That's just going to the same concert. That's just coordinating. That's just saying we want to have the same units. And yeah, we prefer our units. So, before metric was everybody's except for ours. Other places had their own units. They had preferences over the outcomes, but they preferred to coordinate. We do this on a daily. When you make a state, you are essentially making winners and losers all the time. So this Bach or Stravinsky, which is just a coordination problem, right? Bach or Stravinsky is the exact same as the coordination problem, is the exact same as anything else with a different C. They're all the same. They have the same shape. And that similar shape means that we can interpret their equilibria along a continuum. We can interpret their mixing probabilities. The most important thing, however, is that there's 3 equilibria, 2 of which are in pure strategies, and 1 of which is a function of the intensity of the preferences, but the most important thing is just whether it's sort of maybe increasing or decreasing in those, that, P was getting smaller in C and Q was getting bigger in C sort of thing. So that's some intrigue. There's a little bit of intrigue in the game now. There's a little bit of intrigue. You could even kind of imagine on a slider. So let's put this into the PQ space. Let's go. Right? And I'll draw the best response correspondences. So if P is strictly less than 2 plus C, then column player wants to set Q equal to 0. And if P is strictly greater than 1 over 2 plus C, they want to set Q high. They want to set Q all the way equal to 1. And there's that one indifference point. And that indifference point is at 1 over 2 plus C. So as you change C, you're moving this line. Really big C, really small c, really big C, really small c. Actually, it converges to 1/2, right? So if C was 0, we'd be here at 1/2. And if C was really big, we'd be getting closer and closer and closer and closer. We'd be converging, but we'd never get there. Similarly, if Q is strictly greater than 1 plus C over 2 plus C, right? So if it's high, we want to set P high, so we're over here. And if it's low, we want to set P low. And again, this sliding zoom, that's moving up and down in response to the intensity of the preferences. How much this matters to the countries in question as they go through some coordination process together, but they have differing views on how they want to coordinate. If they know they want to coordinate, the more and more that they disagree, the more and more that we're sort of floating in this space. And next thing you know, we've got the two intersections that we'd expect from the pure strategy Nash equilibria, Stravinsky, and Bach. But we've also got this point that just sort of found its way in this fluid space that was influenced by C. As I moved my C slider, I moved all of these lines and dots and intersections. And next thing you know, there was a third equilibrium wiggling in the space that we've made. I could write a sonnet to that. It's wonderful. That's just stupid coordination again. Coordination tells us everything we need to know except for what Prisoner's Dilemma needs to teach us. And apparently chicken is important too, and I promised you we'd talk about it in the C block. So I need to pause to let this disappear. Let's go to the C block. So let's do chicken. Recall again that chicken has two pure strategy Nash equilibria. Much like Bach or Stravinsky, it creates winners and losers, right? So the two pure strategy Nash equilibria are the one where I swerved and you went straight, and the one where you swerved and I went straight. Now, I told you in the B block that you can expect there to be some other equilibrium. If we've only found two, chances are good there's a third somewhere, right? So we need to find that mixed strategy Nash equilibrium. Notice again that because none of us is ever indifferent between our options, there won't be any best responses to mixing that are pure or pure that are mixing. If you knew I was playing a pure strategy, you'd play one. So let's think about what happens if row player swerves with probability P and column player swerves with probability Q. Let's think about row player's expected utility for swerving. Well, with probability Q, they're in a tie, right? They get one happiness point, so Q times 1 plus times, 1 minus Q percent of the time they're just the chicken, and they get 0 happiness points. So the expected utility of swerving is just Q. And the expected utility of going straight, well, with probability Q, they win. They get 2 happiness points for being the winner. So 2 times Q plus 1 minus Q times minus 1. So that all works out to 3Q minus 1. So what's the magical mixing probability that column player could choose to make row player indifferent, which is the only way that row player would want to mix? Well, that's when Q equals 3Q minus 1. Which is just when Q is equal to 1/2. An interesting question is, what would you parameterize here to try to make the probabilities sway? Would you parameterize how awesome winning feels? Would you parameterize how awful losing is? That minus one is what I would hit. Because that's essentially like, that's your disagreement point. And I'd say, well, how bad is a disagreement point? Right? So you could parameterize that pretty easily. And next thing you know, that 1/2 is actually part of a large family of potential options, all of which are decreasing. So if you make that disagreement point worse and worse and worse, if you make the car crash give you worse and worse and worse happiness points, so that the death matters to you more and more and more, relative to all these other numbers, probability of swerving would go to 1. And let's do this all for column player. The expected utility of swerving for column player. Well, with probability P, they're in a tie, so they get 1. And with probability 1 minus P, they're losing, so they get 0. So that's just P. And the expected utility of going straight, well, with probability P, they are the winner, so they get 2. So 2P plus 1 minus P times the minus 1 that they get for the straight. So that works out to 3P minus 1. And again, this all works out to P equals 1/2. Now, the reason I wanted to show you chicken is because it doesn't have the same Pareto thing going on as Bach or Stravinsky did. So chicken is a game with a very different structure. than Bach or Stravinsky. It's not a coordination game. We don't want to coordinate on straight. We don't want that. And because of that, there are different wrinkles in the associated mixing probabilities. So we still have a winner and a loser in the two pure strategy equilibria, but here it turns out that the expected utility of the mixing equilibrium is 1/2 for both players. So it's egalitarian, and it's better than losing. Right? So we can get around this there's a winner, there's a loser, this 2-0-0-2 thing that rubs some people the wrong way. We could get around that if we were willing to introduce the possibility of waste through the car crash, but sort of smooth all of the utility across the whole thing in an egalitarian way. So chicken, this brinkmanship game, what I just said to you is that losing a brinkmanship game is worse than sort of taking your lumps. Now in chicken, I'm not telling you to mix it up in chicken. Do not mix it up. First of all, never play chicken. Promise me that you'll never play chicken. 2, if you do, please play the pure strategy of swerving. Just lose. Just lose chicken. However, if I was talking to a rational robot that lived on a piece of paper or on my whiteboard, it turns out that the expected utility that you get for playing this mixing equilibrium beats losing with risk neutrality. That's like probably a little instantiation of risk acceptance personified, or risk aversion personified. How willing would you have to be, right? So 1/4 of the time right now, 1/2 times 1/2, 1/4 of the time, these two countries are dying in a nuclear war, car crash, James Dean thing. It's all just amalgamated now in my head. So in this mixing equilibrium, 1/4 of these crises go to war. And the expected utility associated with that mixing equilibrium is better than losing. That's kind of heavy when you think about it. It means that we need to kind of pray to the equilibrium selection gods. We need to say to them, please choose the pure strategy, because Pareto isn't even going to be enough for me to rule anything out. You know, in Bach or Stravinsky, it was easy enough to say, you know what, I realize it, but maybe we can come up with another way. You know, we could figure out some way to randomize over the equilibria, or the state would tell us, and we really want them to tell us the pure strategy equilibrium instead of this mixing one. Right? Whether it's cars crashing on the road or musical companions not getting to watch music together, not coordinating is bad. Not coordinating is bad enough that we would be willing to say, create a winner and loser, please. In chicken, no such thing. What? So now we're saying that the same Pareto argument that made it so easy for us to rule out the egalitarian option in Bach or Stravinsky doesn't apply to chicken, where the problem that we're introducing isn't failure to coordinate, right? Isn't not watching music together. The potential downside here is crash. And that's still better because of the structure of the incentives. This is still the games lecture. We're talking about analysis now, but this is still the games lecture. It is the structure of the problem that brings in these interesting wrinkles. I don't know. I'm sorry that I shout at you all so much. But I don't know. There's a lot of cool stuff in there. There's a lot of cool stuff in there, I think. Now, again, I want to highlight the fact that there is no appropriate way to weigh egalitarian instincts against efficiency instincts. None of this is meant to be normative prescriptions. I'm just saying it's not very hard to tell stories where the equilibrium selection argument inherent in the state, or inherent in international institutions, or inherent in treaties, or any other sort of agreement, right? The inherent, we're going to choose this one equilibrium out of many, and we will pay a cost if we fail to live up to that, whether it's by going to jail or not having protection from somebody that I signed a pact with, right? To not being part of the international institution, or seeing them pass some resolution that is worse for you. No matter what, that institution is going to have to make somebody angry in some direction. It's going to have to do something that isn't great. It's going to have some of that Arovian, oh my goodness, I wish that all good things could have gone together, but they don't. And the appropriate way to see that you should talk to people whose opinion you value about that. You shouldn't talk to mine. My job is to help you to see the problem. My job is not to tell you how you feel about the problem. Right? That's up to the people that you love and care about and admire and respect. That's up to the people that teach you normative theories. That's up to a lot of things. Okay, that's not up to me. Charles Barkley. I'm not a role model. Where's Charles Barkley? Get Charles Barkley on my movies. How awesome would that be? None of this is meant to tell you that. It is to say, however, I just thought it'd be really cool to show you these two things that happen a lot in international relations. We need to coordinate, and we might have differing opinions about how we feel about those outcomes. So we're kind of bargaining, but in a cooperative way. Versus, we are pointing our bombs at one another, and we're thinking real hard about shooting. These two strategic situations, you would think that if one of them was going to be the one where you wanted to like say, oh no, we don't want to have the mixing one, you would have thought it was the one that ruled out the shooting. And it wasn't so. Now maybe that's a weakness of Pareto. Maybe that's an issue with efficiency. Maybe that's one way for you to know that efficiency is a shitty criterion. Yes, I said that. Actually, in the other one I bleeped out, I was just saying stupid. This time I actually said it. Wouldn't you have thought that? I would have. I didn't know that until I started thinking about this today. It hadn't occurred to me. So that's mixed strategies. I hope these 3 examples have really helped you to see it. On the problem set, you might have to... Parts where you were nodding along, I mean, I moved a little bit briskly. You may have nodded along a little bit more than I should have let you. And I'm sorry about that. So, any part where you were nodding along today is an opportunity for you to get to your problem set and say, oh crap, I don't know what I was talking about. I shouldn't have been nodding. And ask me questions at meetings or ask Lucy questions or whatever, or on Piazza or anything is fine. I just want you to know that that's just natural. This is just one of those things that seems really procedural and analytic and algorithmic, but it actually isn't. And there are some things that you're going to have to understand, and you can only find the things by digging in the dirt yourself. So that's mixing. Mixed strategy Nash equilibrium, or just Nash equilibrium, since the pure strategies are just a special kind of mixed. It's all about best response. It's all about doing the best thing in anticipation about what's coming at you. And it's also about stability. What's a situation at which nobody would want to deviate? And today's lecture highlights that steady state can mean a lot of different things. Steady state doesn't just have to mean we're playing one profile forever, right? So in the quote-unquote steady state of Matching Pennies, where I was playing heads 1/2 and tails 1/2, and you were playing heads 1/2 and tails 1/2. That's a steady state in a probabilistic sense. We're using the same probability machine every time to tell us what to do. None of us wants to deviate from the probabilities that we've locked in. But if we went to reality, any one of those 4 outcomes would be what happens 1/4 of the time, right? So there's a process that is stable but also random. You see the word stochastic gets used, right? Stochastic, sort of. There's a random part and there's a deterministic part. I don't always like the way that people talk about this, but it's sort of, that's the idea. It's steady, but it's probabilistically steady, right? So like, I wake up, I've got like 3 favorite breakfasts, right? I might not have the same favorite breakfast every time, but I have them in roughly equal proportions all the time. I probably have Belvitas 2 days out of 7. I make poached eggs 3 days out of 7, and I have oatmeal the rest of the time. I already forgot how to subtract away from 7, right? That's a steady state, even though I'm not doing the same thing every time. If you came in on any given day and said, oh, well, Rob had Belvitas today, or Rob had poached eggs today, you wouldn't like suddenly say that I was playing a pure strategy. You just would have had to get more data to see just what the proportions are. But this game isn't repeated. We're not talking about repeated games yet. We haven't talked at all about repetition or time or what happens if we play multiple times together or if you have a chance to observe things about me. This has been 2 countries walk into a bar and they make one simultaneous choice and they leave, right? So there is no multiple observations. There is no multiple chances to see this. There is no repetition, so why the heck am I talking about probabilities? And it's with that in mind that I'd like to conclude with a provocative thought. What is mixing? I know a lot of people that know enough game theory to be able to do mixed strategy Nash equilibrium, right? Some of you are among them now, right? And by week's end, even more of you will be. In a perfect world, it'll be 100% of you, but let's give it time. I know many people who look at mixed strategy Nash equilibrium, are aware of what it is and what it does, they can calculate them, and they still think it's a really stupid idea. Why do they think it's a stupid idea? They think it's a stupid idea because you only play the game once. We only played Matching Pennies once. This is not repeated. This is not over time. We played one time. So what the heck does probability have to do with anything? Because in order for this to work then, let's say that I had worked out 1 plus C over 2 plus C. We were playing Bach and Stravinsky, and we had I guess I was role player, so I needed the probability to be 1 over 2 plus C. So I find out what my C is, I find what that mixing probability is. Let's say it's 1/3. My C is 1. So let's say that I go into playing Bach or Stravinsky with this one time. This one time. Then I have to get out my computer. I can open up R or Python or whatever, and I can have it draw a number. I can have it toss a coin, and 1/3 of the time come up Bach, and 2/3 of the time come up Stravinsky. That's what I'm saying right now. But nobody does that. Even I don't do that. Nobody does that. Nobody in the world does that. Nobody that is mixing in a one-time game, nobody that is mixing in a one-time game actually programs a computer to make this probabilistic decision for them. So what is mixing? Nobody ever lives up to their commitments either, right? In order for this to truly be mixing, then you have to be okay with it. You have to constrain yourself to the probability. You have to promise. You equip your random number generator, whether it's in R or something that you chose, some external factor, whatever that source of randomness is to you, you have to actually commit to it. So if your strategy is, I'm going to wake up, and if it's cloudy out, I'm going to play Bach, and if it's not cloudy, I'm going to play Stravinsky. That's how you randomize. That's the source of randomness in your random strategy. Then you have to actually commit to that. When you get into the car and start driving, you actually have to live up to it. Your hunches can't drive you to a pure strategy in the other direction. So what is mixing? Mixing is a trick. Mixing, as you've seen it so far, is a bit of a trick. It is hard to imagine many decision makers living up to mixing, and that's even beyond the fact that even more decision makers are out there that we think don't mix. Once we've even lopped out the ones that are not reflexive, complete, transitive, continuous, and independent, right? This seems like a new ask. This is a new hurdle. This is a new thing that we're asking of this fake person that lives in their fake world, but we would like them to be realistic, maximally realistic anyway. And this mixing thing seems like we're asking them to exist in like so many different dimensions at once that it seems like maybe we might be wasting our time. And many people are of this view that like if you only have something in mixed strategies, then that isn't really a useful result. Because you're just using the Nash theorem trick to say, all right, I don't have any actual stories to tell, so instead I'm going to tell this mixing story. So what is mixing? Here's a cool result that I can't show you all the way just yet, because there's more to come. We're only halfway in. If I showed you a game like this one, where everybody knows everything about the game, I know the game, I know all my utilities, I know all your utilities, I know that you know that I know that you know, and so on. There is no private information. Everybody knows everything about the game. You know everything about your utilities and my utilities and vice versa. So if I show you a game like this one, the 3 that we analyzed today, and I show you an equilibrium in mixed strategies, 1/3, 2/3, 1 plus C, 2 plus, whatever it is, 1/2, 1/2, 2/3, 1/3, whatever it is. If I showed you that, then I would also be able to, I know that there's another game out there. There's a game that exists that I haven't written down yet. There's a game out there that I don't know about it just yet. I don't know anything about it except for one thing. It has a pure strategy Nash equilibrium that gets all the same essential features as this mixed equilibrium that we think might be a phony. But it has a little bit of private information, a little bit that you don't know about me, and a little bit that I don't know about you. So in other words, this mixed equilibrium, this tricky little thing, this parlor trick that we just did, this probabilistic trick, that doesn't seem like an all the way plausible story, is actually just the current representative of a more plausible equilibrium in pure strategies, an easy story to tell, but where the uncertainty isn't about what I'm going to do, but about which version of me I am. And likewise for you. The uncertainty is not about your Q, because we're going to set a Q equal to a 0 or 1 in this invisible equilibrium that we don't know about just yet. Although we know that it's out there, waiting for us to find it. And what's going on there is pure strategy play is happening, but I don't quite know which you are. I don't quite know your utilities. There's a little bit of uncertainty, not about what you're going to do, but about which version of you are. I'm not trying to be poetic. This is all true. This is true. This is what's going to happen. In a couple weeks, you're going to see there's going to be a slide, and it's going to have a lot of symbols, and you're going to go, oh crap! And on that symbol, if you look hard enough, is going to be that. So you just have to always keep going. You have to stop. You have to enjoy the view. You have to say, this is a beautiful view. I also don't like certain things about it. But that doesn't mean stop going up the mountain. That just means get a better view. Keep going. Now, there won't be such a clean answer for every modeling feature that seems perverse to us, but I think this is an especially useful one, an especially appropriate little story to tell. And I think this is an appropriate juncture because you might be tired right now. I know I am. You might want to stop pushing. But I just showed you the workhorse thing in all of game theory, and there's something a little bit annoying about it. So you got to keep pushing, or you can quit. And then you'll have a half-assed opinion about this. But if you keep pushing, then you get to see this cool little poetic story about some equilibrium that we haven't met yet. His name is Rodney. We don't know anything about him except for the fact that the pure strategies that are played there generate the same things, and there's a little bit of uncertainty about who the players are. They have a little bit of private information. That cool story, you'd be missing out. I think it's worse not to learn the cool story than it is to have the half-assed opinion. So what I mean to say is, seeing all the angles isn't just a matter of being creative and having fun and learning things deeply. That's all part of it too. But it's also just about being able to realize when a commitment that you make is somewhat fluid. When it seems like a big commitment gets made, or it seems like a big assumption got made, or it seemed like a really odd feature got introduced to the model, or something especially implausible, a potential deal breaker got introduced. And there may be legitimate deal breakers, but you should always have your eyes and ears open for potential things to allow us to get out, potential saving graces, or potential new insights that allow us to understand just what are the current problems with how we understand things. But that requires charity. You have to say, I want to see the best case version of this. Now, the best case version of it, I'm not giving you, that means see all the flaws and all of the wrinkles and all the annoyances too. But also, that doesn't mean stop going. So you go and you go and you go and you go until you get to the point where you keep understanding that your commitments are somewhat fluid, and you listen to explanations, and you go and you go and you go and you listen and you go until there isn't anywhere else to go. And very few people are there. None of us are there. But if you were there, if you were to the point where somebody wouldn't be able to say yeah but anymore, be it a believable or an unbelievable yeah but, just something where does not yet exist a yeah but. There are problems out there that do not yet have charitable interpretations. There are things out there where there is not yet a yeah but, where there isn't some story about Rodney the invisible equilibrium. Why did I choose Rodney? And once you're there, then you're truly at the bleeding edge of our current understanding, not just of the problems, but of how we understand them. And once you get to that frontier where there are no yeah buts, and you can see not only the problems, but also the problems with how we understand the problems, and there isn't a yeah but yet, that must be just a magical place. I hope you get there one day. But regardless, thanks for watching.